Okay, now question 2 is asking us about an unfamiliar reaction, which is the reaction of benzene with this compound, cyanogen bromide, in the presence of a gallium bromide catalyst. Now when they ask you about unfamiliar reactions like that, what you should be looking for is analogies, usually very close analogies with reactions you do know about. So what it wanted you to do was to see that that is going to be very similar to bromine. And you do know about how bromine reacts with benzene, and for that reaction you know that it needs an aluminium chloride, or aluminium bromide catalyst, just a halogen carrier. And you were supposed to notice that gallium is in group 3, the same group as aluminium, so it's going to form the same kind of compounds. So gallium bromide is going to be that, and you can see it's closely analogous. So when you're trying to work out, for example, what the equation is, if you can't see it instantly, the thing to do is remind yourself how that one goes. So you just think, okay, benzene plus bromine gives you bromobenzene plus HBr, and hopefully that's a reaction that you're very familiar with and very confident about, and so you just think, oh yeah, this is going to be the same. And so the only difference is going to be that you've got this CN group instead of one of the bromines, but it's going to go the same way. So you're going to make your benzonitrile, and it told you that was the product, so there was no ambiguity there, plus HBr. Make sure you get it the right way around. You could see that the bond must go to the carbon for all sorts of reasons. It shows you there that it's the carbon that's forming the bond to something else. It also gave you C6H5CN, which again suggests the bond is to the carbon. And finally, just counting bonds, you know that carbon's got to form 4, nitrogen's got to form 3. So if you were tempted to write it like this, you should have had all kinds of quality control reasons for thinking, no, that's not right. So CN would be fine, or you could write the triple bond in. Okay, so the next part is now asking us for the mechanism of this reaction. And again, the key to that is to think it's going to be basically the same as the mechanism of bromination. So if you're at all unsure, just scribble that one down first and modify it. So let's just remind you of that if this was bromine reacting, you'd get bromobenzene, and the mechanism of that you've learnt is that your catalyst, the halogen carrier, remember what that always does is it pulls away the halide ion, bromide, Br-, from whatever compound it's catalyzing the reaction of. So in this case it pulls a bromide ion away from bromine to give you AlBr4-, and the important thing is that that leaves behind a positive ion, because remember the positive ion is going to be very attractive to an electron pair, so that's what makes a good electrophile. So in this case Br+, and then that's going to go on and do the attack on the benzene ring because of its positive charge. So that gives you the second stage where you have benzene, here's Br+, and the curly arrow, remember, shows an electron pair moving, and if you remember that's what it is, you'll get it the right way round, because obviously the Br+ isn't going to give away an electron pair, it's going to receive it because it's got a positive charge. So the curly arrow goes like that, and it must point to the atom that's accepting the bond. So it goes to the Br, and that gives you an intermediate, which you hopefully remember well has this slightly odd structure with a hydrogen and a bromine now attached at that position, and then this horseshoe showing that the delocalization now only goes around the other 5 carbons, and the positive charge which was on the bromine is now shared out amongst those, so we draw it like that. And because it wants to get back to being aromatic again, it grabs that pair of electrons from there, which spits out the hydrogen as H+, and restores the aromatic ring. So you get this, with the bromine now in place, and H+ has been eliminated. And the final thing is we've got to make HBr, which is our other product, and we've got to get our catalyst back. And we do both of those things by reacting this H plus with that AlBr4-. So this is the final stage, which completes the reaction. So AlBr4- reacts with H plus and gives us back our AlBr3 catalyst and forms the HBr. So that's the mechanism with bromine. And all you've got to do is to think, right, this is going to be basically the same, but instead of aluminium bromide, we have gallium bromide. But it's a straight swap. It's still group 3, so that's straightforward. And instead of bromine, we have cyanogen bromide. So we have an NC group there instead of a bromine, so that's going to give us the nitrile group on here. And we just go through all the way just saying, well, it's basically the same thing. So this is going to react in exactly the same way with cyanogen bromide. So we can put that in here. And just remember that it always does the same thing. It grabs the halide ion from whatever it's reacting with. So it's still going to grab that Br-, so that bit's the same, except that it's now gallium. But the crucial thing is what it leaves behind once it's pulled that Br- away is that. And so we're going to get not Br+, but Cn+. Okay, so that's now going to be our electrophile. So that feeds into the next bit. And the important thing is that you've now got to think a bit harder about where that curly arrow is going to go. And you know it's got to go to the carbon because in the end it's the carbon that forms the bond. But of course that's also because it's the carbon that has the positive charge. So the best way to draw it is like that. If you really wanted to hedge your bets on where the positive charge was, you could get away with putting a square bracket around it and put the positive charge outside. But the curly arrow must go specifically to the carbon because it goes to the atom that's going to form the new bond. Intermediate's the same, except we have C triple bond N there, and the product's the same except we have C triple bond N here. So you can see how easy this is if you've seen the analogy to the bromine mechanism, because it's exactly the same, and the last step's identical, again except that it's gallium bromide rather than aluminium bromide. So that's the entire mechanism, and the only bit of thinking you had to do was to really see the analogy to the bromine mechanism, which hopefully you've learnt in advance. Okay, so the next part is now asking us about a reaction of benzonitrile, which is the compound we've just been making with 2-chlorobutane, which is this. So butane is a chain of 4, and if it's 2-chlorobutane, then it's that. And you needed to recognise that that is a Friedel-Crafts reaction. So if you have a haloalkane and an aromatic ring, you can couple them together in the presence of a halogen carrier catalyst. So you needed to recognise that it was that kind of a reaction. So the first thing it asks for is suitable conditions, and that is the halogen carrier catalyst. Don't just say that, that's too vague. They want you to name a suitable one, so the obvious answer would be aluminium chloride, which is what people normally use as the halogen carrier in that reaction. And then it says, right, what about the rate of reaction of this compared with benzene when this reaction happens? And the key bit of information it gave you is that this group, the CN group, is electron withdrawing. So you need to know this story, that electron withdrawing groups are deactivating. In other words, they make the ring less reactive than a normal benzene ring would be. So that's the answer to the first bit, that it will react more slowly because the electron withdrawing group deactivates the ring. But it wants you to go further than that because it's a state and explain. We haven't really explained it so far. And so that's about explaining that because it's electron withdrawing, it decreases the electron density in the ring. So we've had electron density again in an earlier question. It's the key concept when we're talking about aromatic reactivity. So the electron withdrawing group decreases the electron density in the ring, and that makes it less attractive to an electrophile, So you can see how similar it was to that explanation we had at the beginning for why the phenol was more reactive, but now we're going in the opposite direction. So electron withdrawing group decreases the electron density and therefore makes it less attractive to an electrophile. And then it asks you what product you get. So there are two issues here. One is to remember the pattern of a Friedel-Crafts reaction, what happens when you actually couple these two things together. But the second is whereabouts on the ring is it going to react. So let's deal with that bit first, get that out of the way. So you have to remember the pattern. When you have an electron donating group, which is OH or NH2, those are the ones you have to specifically remember, they direct to 2, 4 and 6, and you need to know that. When it's an electron withdrawing group, it does the opposite, if you like. It doesn't direct to 2, 4 and 6, it directs to 3 or 5. Usually just one of them, because remember it's deactivated the ring, so chances are it will only react once and just put one substituent on, so 3 or 5 would be the normal rule. So we're expecting that whatever the product is, it's going to be substituted at that position. So the next thing you need to remember is how Friedel-Crafts reactions work, and the easy way to think about that is to remember that all that basically happens is that wherever your halogen is in your haloalkane, when the reaction happens, the halogen is lost because it goes off to form HCl and it gets replaced by the ring. Okay, so it's now a bond not from chlorine to the alkyl chain, but from the benzene ring to the alkyl chain. So it's going to look something like that, and given this relationship, we know then that the CN group is going to be there. The other product is going to be HCl, formed from the hydrogen that was lost from this position and the chlorine that was lost from there. So that's your product.